Hello friends, let's continue discussing crosstalk. We have learned that when a time limited pulse is passed through a band limited channel, it spreads in time and it causes it to overlap with pulses of other message signal, which leads to distortion called crosstalk. A band limited channel can be thought of as a bandpass filter which offers low frequency limitation and high frequency limitation to the signal which is made to pass through it. To study this low frequency and high frequency limitation of the channel, we can model the channel as a high pass filter and a low pass filter respectively. In the previous lecture, we studied the effect of high frequency limitation caused by the channel by modeling it as a low pass filter. In this lecture, we will study the effect of low frequency limitation offered by the channel by modeling it as a high pass filter. A simplest practical high pass filter can be made using simple RC elements as shown here. The time constant RC denoted by tau C here is much larger than the pulse duration capital T. The transfer function for this simple circuit can be directly written as J 2 pi f tau C, where tau C is the time constant R into C, upon 1 plus J 2 pi f tau C. The corresponding magnitude response mod h of f can be written as 2 pi f tau C upon root 1 plus 4 pi square f square tau C squared. Mod h of f is 0 when f is 0. As f increases, this mod h of f increases gradually. For f tending to infinity, mod h of f becomes 1. So we get a characteristic of this sort, which is clearly the characteristic of a high pass filter, a practical high pass filter. So we use this simple high pass filter to study the low frequency limitation offered by the channel to the message signal applied to it. Let us assume that the signal that is applied to this circuit is in the form of rectangular pulses as shown here. Each pulse is of duration capital T. So when a pulse is applied at the input, because the filter is acting as a high pass filter, initially there is an abrupt change from 0 to V, and this abrupt change amounts to a very high frequency component, and therefore the change appears as it is at the output. After that, there is no change, and no change corresponds to zero frequency. The output starts decreasing exponentially, but because the time constant tau C is much larger than capital T as noted here, this tau C is much larger than capital T, this exponential decrease is very slow. At the end of the first pulse interval capital T, the output voltage has reduced from V to some V minus delta, a delta below the original voltage V, and at that time the pulse becomes zero abruptly because it's a rectangular pulse, and that abrupt change again is a very high frequency component, and that appears as it is at the output, and we are here at the output. And again, because there is nothing after that until there is a next pulse, so the output starts decaying very slowly. That variation is exponential but almost constant because the time constant tau C is very large, and therefore it spreads to the next pulse duration, not only to the next pulse duration, but it goes even to higher pulse duration because of very high time constant. If we want to study the amount of crosstalk between the spreading of the first pulse and the second pulse that occurs in the second time slot t plus tau g, where tau g is the guard time, we can study it in terms of the crosstalk factor K, as we had used in the previous lecture also, the area A12 upon A2, where the area A12 is shown here, the overlap area of the spreading of the first pulse to the duration of the second pulse. And A2 is the actual area of the second pulse which occurs here, and for convenience we assume that the second pulse is same as the first pulse. So this is first pulse with area A1 and the second pulse would be here with area A2. We assume that A2 is same as A1, so our crosstalk factor then becomes A12 upon A1. Now A1 is very easy to compute. A1 is simply the area of this rectangle, which is V times T. As far as A12 is concerned, A12 is equal to this delta into this T, because though it is exponential in nature but looks like a straight line parallel to this line, so it looks like this area A12 is that of almost a rectangle with width delta and length T. So it is delta into T. Now we need to compute what is delta. So delta can be computed from here. So delta is this difference V minus delta. So what is V? What is this potential V? So V is simply V e to the power minus T by tau C at T equal to 0, minus what is V minus delta? V minus delta is V e to the power minus T by tau C at T equal to capital T, right? And from here we get delta equal to, when you put T equal to 0 here, this becomes 1, so simply V minus, when you put T equal to capital T, it is V e to the power minus capital T by tau C, and we can take V common from here, so 1 minus e to the power minus T by tau C. We can further simplify it as follows: delta equal to V into 1 minus, now e to the power minus T by tau C can be expanded as 1 minus T by tau C plus T square by 2 tau C square and so on, using exponential series. Now because tau C is much greater than T by tau C is much less than 1, and therefore the higher powers of T by tau C, this is actually T square not tau square, so T square by tau C square, this term and other higher order terms of T by tau C can be neglected, and what we get here is delta is approximately, this one and this one will cancel, so it is simply Vt by tau C. Substituting this delta in the expression of A12 first, delta into T, it becomes A12, which is equal to delta into T becomes Vt by tau C into T, so it is Vt square by tau C, and therefore K, the crosstalk factor, equal to A12 upon A1 is equal to Vt square by tau C upon A1 is Vt. V and V cancel, T square gets cancelled once with this T, and therefore what remains is T by tau C. So this crosstalk factor K is T by tau C. So it depends on the pulse duration T and the time constant of the channel. Of course, this time constant of the channel is not in our hand, but we can control this pulse duration. But as evident from the model that since tau C is much larger than T, this T by tau C is a very small quantity, and therefore the amount of crosstalk in this case, that is low frequency limitation of the channel, is very less, and as such can be neglected, though it occupies many more pulses compared to the high frequency limitation case, where the major overlap, major crosstalk was with the successive pulse only. here the crosstalk may extend to many pulses as shown here because the slow nature of this exponential curve, but that amount of crosstalk is very less. Interestingly, note that no tau g appears here. That is, the amount of crosstalk here is independent of the guard time. So the guard time only affects crosstalk when we talk about the high frequency limitation of the channel. But as far as low frequency limitation is concerned, the guard time does not appear in the expression. So I hope this is clear. So that's all for this lecture. Thank you.